Hyperelastic material properties are obtained using several models that fit curves to experimental data. Hello, I'm Armin. In this tutorial, I'll show you how to add a hyperelastic material from the engineering data sources or import it from a text file and then perform the analysis. Let's take a look at the model details. Hyperelastic materials are a special class of materials that can undergo very large elastic deformations, sometimes hundreds of % strain, and still return to their original shape when unloaded. Unlike linear elastic materials, whose stress-strain relationship follows Hooke's law and remains proportional only for minor strains, hyperelastic materials exhibit a nonlinear elastic response. Common examples include rubber, silicone, polyurethane, natural latex, and soft biological tissues such as arteries or skin. Because of their nonlinear deformation behavior, constants such as Young's modulus and Poisson's ratio lose their linear meaning. They are replaced by parameters derived from the strain energy function, which governs the stress-strain response under any deformation. To mathematically describe their behavior, engineers use strain energy density functions rather than simple constants like Young's modulus or Poisson's ratio. The most well-known hyperelastic models include the Neo-Hookean, Mooney-Rivlin, and Ogden models. The Neo-Hookean model is the simplest, suitable for moderate strains and incompressible rubbers. The Mooney-Rivlin model uses two or more parameters and captures a broader range of strain states. The Ogden model is more flexible and can describe both compressible and incompressible materials, often fitting experimental data for complex elastomers and biological tissues. I'm going to use a sample that is 30 millimeters long, 10 millimeters high, and 3 millimeters thick, with two 4 millimeter radii on the sides. Because the material can undergo large deformations, it's better not to apply fixed or cylindrical supports. Instead, I'll use remote displacement, which works well for nonlinear analysis. One of the two holes is held in place using remote displacement, while the other stretches 100 millimeters the sample along the x direction and twists it 360 degrees. After the solution is complete, I will examine the total deformation and stress distribution on the sample. A simple explanation will be enough. Let's get started with the modeling. To stretch the hyperelastic sample, I need to use a static structural analysis system. First, I double-click on Static Structural in Ansys Workbench. Before setting up the analysis, I need to define the hyperelastic material. For this, I double-click on Engineering Data. By default, the material is set to structural steel, which we do not need here. I'm going to click on Engineering Data Sources to select a material. This library provides several experimental data sets for different materials. I'll choose the Hyperelastic Materials section, where a number of predefined materials are available. I select the elastomer sample, which is suitable for the Mooney-Rivlin model. Now, when I return to the engineering data panel, the elastomer sample has been added. Since structural steel is not required, I delete it. The Mooney-Rivlin model is commonly used for incompressible hyperelastic materials. In this dataset, only uniaxial test data is available, so Mooney-Rivlin is a suitable choice. The hyperelastic toolbox includes several constitutive models. I select the Mooney-Rivlin 5-parameter model, since the elastomer sample is defined for this formulation. This model requires 5 material constants. When I click on Curve Fitting, a chart on the right side shows the uniaxial experimental data. ANSYS can automatically estimate the material parameters. I right-click on Curve Fitting and select Solve Curve Fit. Ansys calculates the 5 parameters and lists them in the property table. The fitted curve matches the experimental data very well. We can also use models with 2, 3, or 9 parameters. Let's try a more accurate model. I right-click on the 5-parameter Mooney-Rivlin model and delete it. Now I select the Mooney-Rivlin 9-parameter model, which generally provides better accuracy. As before, I right-click and select Solve Curve Fit. Again, the fitted curve matches the experimental data very closely. Finally, I right-click on Curve Fitting and select Copy Selected Values to Properties. Now the hyperelastic material is fully defined. We can close the engineering data and move on to the structural setup. Sometimes we need to import experimental data from a text file. To do this, I double-click on Static Structural again and open Engineering Data. I want to define a new material, so I create a new one and name it Hyperelastic. In the toolbox on the left side, the Hyperelastic Experimental Data section is available and contains different types of experimental tests. In this example, I want to calibrate the material using uniaxial, biaxial, and shear test data. I double-click on uniaxial test data, biaxial test data, and shear test data to add them to the material. Now we need to import the experimental data for each test. Let's start with the uniaxial test data. I select uniaxial test data, right-click on the property table, and choose Import Delimited Data. I click on Browse to import the file. At first, the text files are not visible because the default format is CSV. I change the file type to All Files, select the uniaxial data text file, and click Open. 5 rows with 2 columns are added to the table. I check the Import box, assign strain to column A and stress to column B, and set the units to millimeters per millimeter for strain and megapascals for stress. Then I click OK. The uniaxial experimental data is now successfully imported. Now let's move on to the biaxial test data. I select biaxial test data, right-click on the table, and choose Import Delimited Data. I browse to the biaxial data text file and click Open. I repeat the same steps as before. Check the import boxes, assign strain to column A and stress to column B, set the units to millimeters per millimeter and megapascals, and click OK. Only the shear test data remains. I select Shear Test Data, right-click on the table, and choose Import Delimited Data. All required experimental test data has now been imported. Next, we can calibrate the hyperelastic material model using the experimental data. For incompressible materials, we can use models such as Mooney-Rivlin or Ogden. In this example, I select the Mooney-Rivlin 5-parameter model. In the property table, I right-click on Curve Fitting and select Solve Curve Fit. Ansys calculates the material parameters using all imported test data. To finalize the material definition, I right-click again and select Copy Calculated Values to Properties. The hyperelastic material is now defined correctly. We can close the engineering data and continue with the analysis setup. In the next step, I import the geometry into the system to run a hyperelastic simulation. I right-click on Geometry, select Geometry CAD file from the menu, and then double-click on the model. Now we are in Ansys Mechanical. The first task is to assign a hyperelastic material to the part. When I expand the Geometry branch, I can see that the default material is structural steel. I click the Material drop-down menu and select Hyperelastic. Next, I move on to the Mesh setup. I collapse the Geometry node and select the Mesh. Here, I can see the default element size and physics preferences. For this type of analysis, it is better to set the physics to nonlinear mechanical, although this is not strictly required. A 1 mm element size is sufficient for this simulation. I right-click on Mesh and select Generate Mesh. As you can see, the mesh is somewhat coarse, but it is adequate for our purposes. Now, let's define the boundary conditions. I right-click on Static Structural and open the Insert menu. For nonlinear mechanical simulations, it is better to avoid fixed support, standard displacement, frictionless support, or cylindrical support. Instead, using remote displacement provides better numerical stability. First, I apply a remote displacement to the first hole. I select Remote Displacement, choose the hole, and click Apply. The coordinate system is automatically set to the center of the hole. In the definition, I fix all translational and rotational degrees of freedom by setting them to 0. I also change the behavior from deformable to rigid. Next, I apply a second remote displacement to stretch the sample. I insert another remote displacement, select the second hole, and click Apply. In the definition, I apply a 20 mm displacement in the x direction. Since the total sample length is 30 mm, this amount of stretch is reasonable. All other directions are set to 0, and the behavior is again changed to rigid. Finally, I adjust the analysis settings. I click Analysis Settings, then go to Solver Controls. Because hyperelastic materials exhibit large nonlinear deformations, I enable the Large Deflection option. Next, I turn on Auto Time Stepping by changing it from Program-Controlled to On. I then define the following values: initial substeps 20, minimum substeps 20, maximum substeps 500. These are relatively high substep counts, but they improve convergence and stability, especially for nonlinear hyperelastic problems. Now everything looks good, so let's quickly review the setup before solving. The material is hyperelastic, the mesh size is 1 mm, and nonlinear mechanical behavior is active. For the boundary conditions, the first hole is fully fixed using a remote displacement, and the second hole is stretched in the x direction by 20 mm. Now, let's solve the model. The solution doesn't converge because the mesh quality is not sufficient for large deformations. To improve stability, I reduce the applied displacement to 15 mm. In hyperelastic analyses, the mesh must be defined carefully, especially around the holes where element distortion is more likely to occur. Now we'll run the solution again. With 20 mm of displacement, the solution fails, but with 15 mm, it completes successfully. Now let's look at the results. From the solution branch, I insert total deformation and then add equivalent von Mises stress. Finally, right-click on the solution and choose Evaluate All Results. I'm going to click on Total Deformation, select the side view, and play the animation. We can see the deformation clearly. Some elements around the holes are distorted, which means that applying excessive stretch can lead to numerical divergence. Now let's check the von Mises stress. The maximum stress appears in the x direction, which is reasonable. Next, let's add a twisting deformation to the sample. I go to Analysis Settings and increase the number of steps from 1 to 2. Then I set the current step to step 2 and enable auto time stepping again. For this step, I use the following values: initial substeps 25, minimum substeps 25, maximum substeps 1000. Now I'll return to remote displacement 2, where the tabular data runs from 0 to 2 seconds. In step 1, the sample is stretched 15 millimeters in the x direction. In step 2, I keep the 15 millimeter stretch and apply a 360-degree rotation around the x-axis. For better numerical stability, I reduce the stretch to 10 millimeters. Now let's solve the model again. Right-click on the static structural and click Solve. This time, the solution completes successfully. Now let's check the results by clicking Total Deformation and playing the animation. As you can see, the sample stretches during the first step and then performs one full rotation in the second step. The simulation time and boundary conditions can be changed based on our requirements. We can also inspect the equivalent stress distribution. The maximum stress is about 15 megapascals, element distortion is limited, and the simulation runs smoothly without convergence issues. This brings us to the end of the tutorial. Thank you for watching. If you found this helpful, please like the video and subscribe to my channel for more ANSYS tutorials.